Welcome back to Advanced Topics in Astronomy. So today we are continuing with black holes and diving ever deeper into this particular topic. So last class, before the midterm, which hopefully you survived because you're still here. So before the midterm, we were talking about black holes and what defines them. And what defines them is basically their event horizon, is the fact that there is a certain distance from which it is inescapable because the escape speed rises higher than the speed of light, and nothing can do that. So do you remember what is the Schwarzschild radius, or in other words, sorry, actually no, what is the Schwarzschild radius for a 3 solar mass black hole? So you just multiply by 3, so it's 9 kilometers. And I almost gave away my next question. The event horizon's radius is A, bigger, B, smaller, or C, the same as the size of the Schwarzschild radius? It is the same. It is a different name. Okay, so the Schwarzschild radius is the distance from the singularity, is the distance from the center of the black hole from which you cannot escape. The size of the event horizon, the radius of that is the Schwarzschild radius. So the event horizon is our way of describing the region from which within you cannot escape, or you can't see anything happening either. So today we are continuing with black holes. We're going to look at how they affect space-time. We're going to talk about what we can actually measure from a black hole, because they mostly seem like a black hole of information, right? But there is some amount of material or some amount of information that we can get from it. What would it look like to enter a black hole? That's an interesting one. And how exactly would you die? Because I think we can all accept you would die. So how exactly would you die entering a black hole is an interesting question. But what we're going to start with is what I left off with just before we took the break for the midterm. And that was the idea that a black hole can evaporate. So Hawking radiation can allow a black hole to evaporate. What does that mean? The essence of Hawking radiation is something that we've talked about before. It's that if you collide matter and antimatter, they will annihilate completely to give you pure energy in the form of probably gamma rays. So for example, in picture A there, we see an electron, the blue, and the red anti-electron, which is also called a positron, which is everything the same as an electron, but it has a positive charge instead of. And so when they collide, they completely annihilate and turn from matter into energy. That's annihilation. On the other hand, you can have production, where if you have enough energy in one spot, so for example, if a bunch of gamma rays come together, then the exact opposite of picture A can happen in picture B. If you have gamma rays, or in other words, enough energy come together in one spot, then poof, it can become matter, energy into matter. And you get a matter-antimatter pair. So you get pair production or pair annihilation. And we talked about this a little bit before. This is something that happened during the, what was it, the particle era, I believe, after the Big Bang. Okay, so here's a couple questions. Matter hitting matter will do A, annihilation, B, production, or C, neither? And I bet a lot of you are saying annihilation, but reread that question. Matter hitting matter. Have you ever hit matter? Did it annihilate you? No, you're hitting matter right now. So no, it's a trick question, I'll admit, but come on. Matter hitting matter. If you punch someone in the face, they don't annihilate, unless, I don't know, what are you, One Punch Man? Anyway, so the answer is C, neither. Fine, let me change the question. Matter hitting antimatter will do what? Annihilation. Annihilation creates a matter, B, light, or C, nothing. And the answer is light. Not visible light, gamma rays, but that's still light. Annihilation doesn't give you nothing, okay? It's not possible to turn matter into nothing or energy into nothing. Energy is conserved, and so is matter. But they can go back and forth. E equals mc squared. Mass and energy are related, and they can turn into each other. So annihilation will turn matter into light. Now, it is possible to pair these up. What if you have energy flying around in a very highly energetic environment, and then poof, it just turns into a pair. It produces a pair, an electron-anti-electron pair, and then, hey, one's negative, one's positive. Are they attracted or repelled? Opposites attract, right? So they will attract each other back together and annihilate to give you your energy back. And so you might not even have seen anything happen. in this situation, right? You blink and you miss it. That this pair production happened and then it disappeared again and annihilated back into energy. So it's almost like nothing happened, but not quite, all right? So in a high enough energy environment, this pair production and annihilation can happen all the time. Here's an idea for a high energy environment around a black hole. So the idea of Hawking radiation is that in the vicinity of a black hole, if you have this sort of thing happen, then instead of re-annihilating back into energy, the produced pair and antipair, or particle and antiparticle, I guess, one of them could fall into the event horizon. And if that happens, it can't escape, but the other one still can. And so it's possible for this to be happening in the vicinity of a black hole, because that is a high energy environment for sure. And if that happens and one particle falls in and the other doesn't, if it stays just outside the event horizon, then it can actually escape, whereas the other doesn't. And so it'll look like a bunch of particles or antiparticles or whatever, a bunch of particles are moving away from the event horizon. That's what it'll look like. It looks like the black hole is radiating particles away. Now, is anything actually escaping from within the event horizon in this situation? From within the event horizon? No, something is falling in, that's all. Nothing is coming out, all right? Nonetheless, as things escape from the vicinity of the black hole, they are removing energy from that environment. And when you remove energy, you remove mass. So if enough energy, and it seems weird because nothing's leaving the event horizon, but nonetheless, if you are removing energy from this system, then you are making it less energetic, you are making it less massive, and the black hole can shrink or evaporate away, even though nothing is leaving, which is a pretty funky concept, but not the weirdest one we're going to confront today. So evaporation is a loss of energy and mass, and that means the black hole will gradually shrink and shrink and shrink. Now, it turns out that this is not all that important. It's not all that potent unless you have a really, really small black hole, right? The smaller the black hole, the more substantial this evaporation will be. And keep in mind, if you're feeding the black hole anything, it's probably going to keep growing, even if it is evaporating a little bit, right? Overall, I mean, frankly, even if it's an empty space, there's no space so empty that it isn't full of the cosmic microwave background radiation left behind by the Big Bang. So at the very least, any black hole sitting in space will be devouring CMB energy. So it has to radiate away more than that if it actually wants to shrink overall instead of grow overall. So in order to get a black hole so small that it'll actually evaporate effectively enough to shrink, you apparently need one that is smaller than the smaller than the mass of the moon. Now, we talked about how black holes form, of course. What is the lowest mass black hole you would ever expect to find? White dwarfs are up to 1.4 solar masses. Neutron stars are up to 3 solar masses. Anything bigger than that as a corpse would be a black hole. So the smallest black hole you would ever expect to find is 3 solar masses. Where the heck do you get one that's smaller than the mass of the moon? I don't know. Any ideas? So apparently a car mass black hole will evaporate in something like a nanosecond. A car mass black hole is just gone before you can blink. So yeah, as they get smaller, their evaporation becomes more effective, but for stellar mass black holes, they'll never be small enough to really evaporate effectively. So this may happen, Hawking radiation may happen, although, by the way, we've never detected it. The math says it'll happen, and we do think it will happen. So Hawking radiation may be coming off the black hole, but overall, any normal black hole will continue to grow and not really evaporate from that. All right. So the smallest stellar black hole, again, 3 solar masses, is not really going to be shrinking because of this, even if it is emitting some Hawking radiation. But we did talk about the idea that there could be mini black holes. Remember, we said that when the Large Hadron Collider was turned on, people worried that particles could be smashed together at such high energy that they would produce little mini black holes. And that we don't think really happens. And if it did, they would evaporate super fast. So we wouldn't even know they happened. But there is another possibility. Right after the Big Bang, there's a high energy environment for you, right? Right after the Big Bang, there was a very high energy environment. And during the moment of inflation, material got picked up and swept out faster than the speed of light as space expanded or inflated faster than the speed of light. So it is possible that material got ultra compressed and could have formed enough energy in one place to make mini black holes. These are called primordial mini black holes because primordial is a word for, right after the start of things. So it is possible that right after the Big Bang, the universe might have been full for just a brief time of many primordial mini black holes. If that's the case, then, and we don't know, this is theoretical only, but if that's the case, then they all would have evaporated very fast. And so the early universe might have actually been suffused with quite a lot of Hawking radiation from the rapid evaporation of these mini black holes. If there's some way that we could detect that, then it would be our first real detection of Hawking radiation, for starters, but it would also confirm that such a thing can actually exist, which would be amazing. Unfortunately, that's something that happened 13.8 billion years ago. The Hawking radiation would have to travel 13.8 billion light years to get to us, or more. So, yeah, I don't think we're going to be discovering that anytime soon, but if we can figure out a way, it would be pretty amazing. These primordial mini black holes would have the mass of the planet, our planet, a radius of a centimeter. They're cute, but as massive as Earth. I don't suggest you actually pick one up. Now, the trick with all this is something that was mentioned in a video in, I think, our second lesson when we watched a Kurzgesagt video on string theory. And what was mentioned there towards the end was that gravity and quantum mechanics do not work well together. Because quantum mechanics is all about the iffiness of things, whereas general relativity is all about precise measuring of space-time. They don't work well together. Quantum mechanics said that the particles are the players and gravity is the stage, right? If you remember that from the video. So the problem is that this doesn't really seem to work from some interpretations. So in 2012, there was some work came out that said that when one particle falls in and the other stays out, there's a property called quantum entanglement, which you may have heard about before. It's related to the idea that things can teleport, which is true. Particles that are born together are quantum entangled, and when one falls in and the other doesn't, that entanglement is broken, and that releases quite a lot of energy, the energy of the entanglement. And so the amount of energy released from all this stuff going on at the event horizon would apparently turn the event horizon into what they called a firewall. Huge amounts of energy being released from this entanglement being broken. And so the event horizon would be a very much more dramatic place than we were thinking. We think it's just pretty much a boundary in space that you wouldn't even notice as you crossed it. But if this is correct, the production of Hawking radiation would produce huge amounts of energy, causing the event horizon to be a devastatingly energetic environment. So in 2014, a couple of years later, Stephen Hawking, who has since passed away, but Stephen Hawking came back and he said, okay, I don't think that's quite right. The truth is we don't understand how quantum mechanics governs the particles. General relativity governs the gravity of the event horizon, and they don't work together very well. So how are you supposed to calculate what's going to happen to a quantum particle in a high energy, high gravity environment like that? Hawking said we can't. So we don't know exactly what's going to be going on at the event horizon. We do still think that Hawking radiation will happen, but we don't know exactly what that'll do for the particles. So what Hawking said is the event horizon as we know it is not correct. Our math for it is not right, so we do not truly understand the event horizon. And so some people in the media took this and ran with it, and so we got this incredibly stupid title. Stephen Hawking says there are no black holes. Oh dear, the media. Oh, the media. They have and this is in Nature of all things. And this person wrote this. There are black holes. There are black holes. We can observe them. there are black holes. What he meant is that our mathematical understanding is not sufficient to the task. So we don't understand them properly. There are no black holes the way we calculate them now. And yet the title here is There Are No Black Holes. I don't remember exactly what this Nature article said. I'm so busy mocking it. I'm sure the Nature article probably explained that well enough, but you can imagine that, idiots on Reddit took and ran with it and was like, aha, there are no such things as black holes now. Take that, science. No, there are black holes, of course, as we're going to talk about. We can find and measure many black holes. It's just that we don't understand exactly what's going on, which shouldn't really be a surprise anyway, frankly. Okay, so moving on. Anyway, and by the way, I haven't seen anything further on that debate in years, so I don't know. I don't exactly know what's going on there. But anyway, so what we're going to talk about now is a black hole's effect on space and time. So here, is this real? I wish. This is a computer simulation of a black hole passing between us and, I don't know, is it a galaxy or something? And what you can see is lensing and just like moving a lens over a piece of paper, things are very distorted. So the background past the black hole gets very distorted. So let's talk a little bit more about lensing. We've talked a little bit about it already, but let's review it again. So Isaac Newton, in the 1600s, gave us his law of gravity, which is that two masses will attract each other from a distance based on the constant of gravity, g, their masses, divided by the distance squared. So nothing actually connects them at all. There is no connection. They aren't touching. So it might seem a little weird that they can feel each other anyway. Action at a distance. Then along comes Einstein. And Einstein showed that Newton was not exactly wrong, but Einstein came up with something better. Now, just to set the stage a little bit for this, Newton is, regarded as one of the greatest scientists of all time. And he was an Englishman, and so the English were very proud of Newton. He was their boy for 300 years. His view of gravity held, and it was perfectly good. And then along comes, in the 1910s, a little German guy. I don't know if you know anything about history, but the 1910s Germany was not that popular in some ways. So along comes a little German guy saying that he's got something better than Newton. You better believe the English were pissed. Einstein did not become famous overnight. That's for sure. It took some time and it took some pushback. Anyway, so Einstein proposed that gravity is actually not a force between two masses at all. Newton's law works, make no mistake. It works perfectly well. We will be using Newton's law until the end of time. But what's actually happening is that each mass causes a warping of space-time, curves space-time. And every other mass will move through that distorted space-time on a straight line. But since the space-time is curved, it will end up curving with space-time. And so things will take a curved path. So if you have a comet flying by the sun, then it will bank as it curves. You ever seen, like, frankly, even on a highway, if you ever driven on a highway and you see the road banks a little bit, it turns when you're making a turn. Or certainly on a racetrack where the cars are going very fast, the racetrack will bank quite heavily. And so that way the cars can drive in more or less a straight line, but when they drive in a straight line along a banked surface, they bank with it, they turn. So the comet is moving on a straight line path, but it's space itself. It's the material, the paper, I guess, that it's moving along that is actually curved. And so it'll follow that and curve. So a comet will curve as it passes the sun. If you get things going just the right way, then you can actually get them to orbit the sun. So this analogy, the rubber sheet analogy, is the idea that you take a bowling ball, you put it on a trampoline or something like that, and you'll see it causes a depression into the trampoline surface. And if you roll a ball past that, then the ball will curve as it moves along on the curved surface. And that works. It actually works very well. As an analogy, the rubber sheet. We don't live on a rubber sheet. I don't know if you've noticed this, Might be fun if we did, but we don't live on a rubber sheet. We live in 3D space. It's a little harder to picture how this is happening in 3D space, but it does. So here's an analogy. Have you ever seen one of these donation funnels? They've got them at like the science center in the zoo, where you stick a coin on the rim and then it sort of rolls around and it spirals in. And the reason why it's spiraling in is because there's friction, so it loses energy and it spirals in. The Earth, there's no friction in space, so the Earth will continue to orbit the sun forever, not spiraling in at all. In an accretion disk, there is friction and things do spiral in, right? Anyway, so yeah, if you've ever seen one of those donation funnels, that's basically what's happening. Is the coin is doing an orbit. I remember at the zoo trying to show my daughter this once. I think she was like 1.5. Why was I trying to explain general relativity? Anyway, this is what happens. I put a coin on and it just fell over and it slid straight down. Damn it! That was a quarter. Why didn't I use a penny? Oh, anyway. So yeah, and notice, by the way, in the picture of the sun and the Earth, the sun creates a depression. The Earth does too, right? The moon rolls around in that depression, and the sun is affected by the Earth's depression too. Depression has wide-ranging impacts. Anyway, so as soon as Einstein proposed this, of course, trying to dethrone the god of science, Newton, you better believe there was some pushback, and he was told, well, you better have some proof of this, right? And so the first proof, the easiest proof, was the orbit of Mercury. The orbit of Mercury. For 300 years, we understood how orbits work, thanks to Kepler, and then who gave us the laws of orbits, and then Newton explained what causes it, gravity. So there was no surprise to orbits. But Mercury's orbit, and frankly all the orbits, but especially Mercury, does this thing called precession. And Newton's law never explained precession. What you can see is that Mercury's orbit is not a perfect circle. No orbit is. All orbits are ellipses. They have a long axis. And so what happens is, as Mercury goes along on its orbit, the long axis of that ellipse gradually moves and sort of goes around as well. And so each time Mercury goes around, it's going to go around in a slightly different way as the long axis precesses. And so it'll create sort of like the pattern of the petals on a flower or something. And precession is what happens whenever you have something on a curved surface, or whenever you have something spinning on a surface with a tilt. Then, like if you spin a top, for example, or a dreidel, if you spin that, then you'll watch the axis of rotation gradually move around and point in different directions, and that's precession as well. So anyway, this happens because Mercury is orbiting on a curved surface, curved spacetime. So Einstein went ahead and he plugged Mercury's numbers into general relativity, his calculation of gravity, and lo and behold, it explained precession. Boom, just like that. He could understand why Mercury precesses, a 300-year-old mystery that Newton's law cannot explain, explained in an afternoon by Einstein and general relativity. So pretty cool. Now, people still did not 100% buy it, all right? It was still a little German guy trying to shoot down the god of science. So it was actually an Englishman who went and proved that Einstein was correct. So I think his name is Arthur. Anyway, Eddington, I think it's Arthur Eddington. There's a movie about this, by the way, called Einstein and Eddington, starring Andy Serkis and David Tennant, which is really good if you can watch it. Anyway, so Eddington wanted to show that Einstein was correct, or prove if he was wrong, for that matter. And so the idea was this. According to Newton, light has no mass. Light will just fly straight by the sun, no bending. According to Einstein, as light passes a massive object, it will move on a straight line just like it always does. But since the surface that it's moving through is curved, it will curve with it. It will move on its straight line, but just like a car moving in a straight line along a banked road will bank, the light will bank as it moves along past something like the sun. So what we needed to do then was, and what Eddington came up with, is we need to look from the Earth past the sun to the stars at its rim. Now, how do you do this, though? How do you do this? The problem is you can't see the stars when the sun is out. And if the sun is not out, then Well, you need to be looking right past the sun. What he came up with is, let's look during a total solar eclipse. During a total solar eclipse, the moon blocks the light from the sun. And during that instant, you can see the stars around the sun. So what happens here with gravitational lensing is, let's say you've got an object directly behind the massive object. So here's us, massive object, and this thing is directly behind it. We may or may not actually be able to see it just past the sun. Keep in mind that this is an analogy. The sun is not actually sunk down. But anyway, as light moves from that massive object off in this direction, or from that real blue object off in this direction, it will bend as it passes the sun and come to us from this angle. And so us here on Earth, we will look out in this direction. We'll say, oh, look, there's light coming from this direction, so there must be a blue object over there. We will see an image, a mirage of a real object. There is nothing there, but we will see one. Similarly, on the other side, light will bend coming this way, and so we will say, oh, look off in that direction. If you look off in that direction, there's another blue object, and lo and behold, they look identical. Two images of the same thing. How odd. Neither one is real. They are a mirage. Have you ever seen a mirage on a hot day on the highway, for example? You're driving along and you look into the road and you can see the sky in the road. And it's because the light from the sky is bending through the hot air over the road and ends up coming towards you from below. And so you see the sky in the road. That's a mirage. And these are effectively mirages. So what Eddington came up with is, he's going to go look at the sun during a total solar eclipse, and we know where stars should normally be, of course, because we can just look at them at night when the sun is just totally out of the way. But when the sun is in the way, but blacked out so it's not glaring, when the sun is in the way, we're going to see that some of the stars around the sun are in slightly the wrong spot. That's what he did. He went all the way down to Africa for a total solar eclipse. It was a pulse pounding 2 minutes where he managed to get, I think, something like 4 or 5 pictures. But he saw that the stars had moved. They were in the wrong places. They were slightly displaced. The light from them had bent as it passed the sun, and therefore Einstein was correct after all. And he had proven that gravitational lensing happens. So here we see a galaxy cluster, for example, and check it out. Look at that, circled in blue. We see identical things, identical. That's not right. You don't find identical things all that often in space, unless they're mirages. Okay, so what we're looking at here is a bunch of mirages of a real thing that we may or may not even be able to see off in the distance, but there's enough mass from this galaxy cluster that it's warping the light from this background object, and so the background object ends up looking, and it is actually a blue thing, isn't it? It ends up looking like it's in multiple places on the sky, which is pretty neat. Now keep in mind, this is 3D. I think there's a problem that I end up showing you the rubber sheet analogy too much. And the rubber sheet analogy is always shown so much. But it's not true. We don't live on a rubber sheet. We live in 3D space. But how do I show you curved 3D space? Right? That's tough. So here's a good one. I think this is the only good image I've ever seen that really does it. Where if you take a grid, like a regular rectangular grid, right, cubical grid, like a Rubik's Cube, and then you stick a star in the middle of it, or whatever, a cluster of galaxies, or a galaxy, or whatever. You stick something in the middle of it with mass, then what you can see is that the grid becomes distorted. It is falling towards the mass from all directions. Notice that the top of this cube looks like the distorted rubber sheet. The side of the cube, each side of the cube, looks like a distorted rubber sheet. This time the rubber sheet, again, is falling towards the central object. And even below, it's falling towards the central object from all directions. Space is falling towards the thing. So you can see the curved effect of space, even in 3D. And do you notice something else in this animation? Do you notice the clocks? We're going to come back to this, but notice that the clocks far from the mass are just ticking around fast, 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 whereas the clocks close to the mass are slow. Time slows down as you near a mass, because don't forget, we're warping space-time. But we're going to come back to that a little bit later. So here we see a picture of real gravitational lensing in the sky. Just Google image search galaxy cluster. Any picture you find of a galaxy cluster, you will see often. Look at this blue thing. Identical blue things. There, maybe in the center here, maybe there. Identical blue things. I don't know why they're always blue, but they don't have to be. But yeah, mirages. All of these are mirages. Right? We can see them. This is a real picture, but there's nothing actually there. It's just that light is so bent, so distorted, that we end up seeing things like in a funhouse mirror, but really a funhouse lens, and everything looks really, really weird. Here we see another one. Notice the smears that you get here. Again, Google image search any galaxy cluster, and you will see these sorts of smears if you can zoom in enough. You see these smears all the way along. Look at that. Look at that. This is a real picture. Those are real smears. There's obviously nothing shaped like that floating in space. So it's a little bit like scratches on a lens, actually, right? Is that here's this massive galaxy cluster, a cluster of hundreds of galaxies. It's one of the biggest places we know of. And when light from anything far in the background comes to us, it can end up distorted and flattened out like this into this broad smear, which is pretty neat. It's a real picture. Here's an example where something in the background, which again happens to be blue, something in the background is being so lensed by the foreground object, we probably can't even see the background thing. It's probably directly behind this. But the light from it is coming to us from almost all the way around. It's almost a total Einstein ring, which is pretty wild. That's a real picture, right? So coming back to this animation, you can kind of see that when a black hole, which of course is an extremely dense source of gravity, when a black hole comes between us and a light source, it warps things just like that, and you get the smear. You can make an Einstein ring for yourself. Just take a lens or even a wine stem, right? The stem of a wine glass moved over a black smudge. And oh, I can't see the black smudge anymore, but I can see the Einstein ring, right? Everything gets distorted. It helps if you drink the wine first, but everything gets distorted when you look through the bottom of the wine glass, because that's lensing. That's a lens of glass. This is a lens of gravity. Still works. Oop, too far. Okay, so again, black holes will of course be an excellent example of how this can happen. All right. So let's say the sun creates a depression in space-time. If you take the same mass but collapse it even more, make it even denser, then it will push deeper into space-time and create a deeper depression. A neutron star even more so. Think about it this way. If you're walking on thin ice on a frozen lake, then what you would do is you would try and spread your weight apart, right? Maybe even slide around on your stomach with your weight spread as far apart as possible. That's what snowshoes are for as well, is to spread your weight out. On the other hand, if you really want to puncture a surface, stand on your tippy toes, right? And then you'll go right through the ice. So this is the idea of pressure, is you put how much weight into one spot. The smaller and smaller the spot that you put all the weight, the greater the pressure on that one point. And so if you stand on a trampoline with your legs spread, you won't sink all that deep into it. But if you bring your legs together and you stand on a single tiny, tiny spot, you will push a lot deeper into the trampoline. So if I take a 1 solar mass weight or whatever, and I shrink it and shrink it and shrink it, it'll push deeper and deeper and deeper as it's sitting on a smaller and smaller spot, until eventually with a black hole scenario, it pushes all the way down to the extent that at some point, the walls of the depression, at the event horizon, the walls of the depression become vertical. Vertical? Straight up and down? That means this is effectively, truly a bottomless pit. That's another way that makes the event horizon special. That's why light cannot escape it. Light can move up a curved surface, but it can't move up a vertical surface. Again, in the analogy of a 2D sheet, right? So that's another way to mathematically describe the event horizon, is it is where space-time becomes infinitely curved. So here's a slightly more schematic view of that. Let's take the sun, and what we're going to do is we are going to compress the sun to make it a white dwarf and then a black hole. And of course, that's not going to happen And what we're doing is we're keeping the mass the same, we're just shrinking it. So again, you can't do that. There's no real way to do that. But if I had, a magic wand or an infinity gauntlet or something, and I shrink the sun, then how would it push deeper into space-time? So here's the curvature of space-time that the sun produces today. This here is the edge of the sun right now. You could fly your spaceship as close as you want until you catch fire and die right at the edge of the sun. But obviously you can't go inside the sun. If you collapse the sun down to the point of a white dwarf, so it's now planet-sized, 100 times smaller radius, then it will create a much deeper indentation into space-time. If you collapse it all the way down to make it a black hole, then that indentation will end up becoming infinitely deep. And you have punctured space-time. You have created a true exit from our universe by puncturing space-time. You go in, you don't come back out. So here's my question for you. This ring right here that I'm pointing to, this ring, is the curvature of that ring changing when we compress the sun? Is the effect of the sun at that location changing at all as we compress the sun? What do you think? Yes or no? Take a close look at the picture. No. No. Outside the sun is not changing at all. Gravity is still the exact same out there. It's just that as you compress the sun, it's sort of like you're revealing new space-time, right? So like you can't get in here right now, but if you compress the sun down, then you could. You can keep going in, and the keep going in that you've revealed is a very deep hole. That's not there right now because the sun is not that compressed. But if you compress the sun, then it's like that's what's happening, is you're unveiling a deeper and deeper pit. But the space-time out here is not changing at all. Now, does this ring about? There's something I'm thinking about that this kind of explains again from last class. I asked you a question, previous class before the midterm, about exactly this sort of situation. Do you know what I'm thinking about? I asked you what would happen to the Earth's orbit if the sun collapsed to make a black hole. And the answer was nothing. Nothing would happen to the Earth's orbit. And this is a graphical representation of that answer. Nothing would happen because the gravity out here is not changing, because the central mass is the same, right? So the gravity out here is not changing. You're revealing a smaller region that you can explore more, but out here, nothing is changing because gravity is not changing because the central mass is not changing. And so orbits out here would not be changed if the sun became a black hole, right? And again, that's the exact same thing we said previous class, but this time sort of this is a picture of it, right? Now, what happens if you go down that bottomless pit? Well, wouldn't we all love to know? Remember I mentioned that as a black hole collapses, once it collapses within its own event horizon, then it's gone. There's no way to know what happens in there after that. It is possible that it does not keep collapsing at all, but likely it keeps collapsing all the way down until it becomes a singularity. All that mass collapsing into a single point, infinitely dense, right? Mass divided by 0 volume. Good luck calculating that on your calculator. Infinitely dense, a singularity. And the singularity will lie at the bottom of this gravitational well, but you'll never reach it. And even if you did, you'd never get back to tell us what it's like. And so we have a problem understanding what goes on inside a black hole. I mentioned before the problem with the firewall, right? That we don't even really know what happens at the event horizon, but it gets worse as you go inside, right? We'll never know because nothing comes out. No information comes out, nothing from within a black hole. So there's no way to know from within an event horizon. So there's no way to know. In a way, this almost sounds anti-scientific to talk about something that we know we'll never be able to investigate. But, well, there are ways mathematically that we can talk about it. But yeah, we're never really going to get in there. As a result, it's very good for science fiction, right? Science fiction loves when we don't understand something and you can say, oh, maybe this happens, right? So if you've seen Interstellar, for example, Spoiler alert if you haven't, but if you've seen Interstellar, for example, it turns out that the inside of a black hole is Matthew McConaughey's little girl's bedroom. I don't know, maybe. Seems unlikely, but maybe. Who knows what's inside a black hole, right? But since it is puncturing space-time, you get some very interesting possibilities. So here's an interesting possibility. You could make a wormhole. A wormhole is the idea that if space is curved, and it is, then maybe it's possible to curve 3D space into the fourth dimension, into the bulk or the hyperspace, to curve 3D space through the fourth dimension such that, let's say, a distant star like Vega is actually really close to us if we could just cut through hyperspace. So Vega is normally 25 light years away from us, and traveling there at the speed of light would take 25 years. We can't do the speed of light, so I don't think we're ever really going to get to Vega. But if we could curve space so that Vega is really close to us through the fourth dimension, and then drill towards it, puncture space-time using a black hole, puncture back out at Vega, we have drilled a wormhole. Just like an apple can have a wormhole drilled in it from surface to surface. But we would have drilled a wormhole to Vega. Nothing would be different from our perspective. We would still look 25 light years straight out in that direction to see Vega. But if you go through the wormhole, you would find out that Vega is just one step away, or however big the wormhole would be, which is pretty cool. So in a way, you get to cheat, and it's almost like you're going faster than light, or superluminal. You're not really beating light speed, though. You're just cheating, right? You're not winning the race. You're just skipping straight to the end from a shortcut. But this may be one of the only ways to drill a wormhole like this, would be one of the only ways that we could ever travel super far through space. We will talk more about this in our last couple classes. But is it possible? Is such a thing possible? Well, we better hope it is, because again, getting to Vega would take 25 years at light speed. Alpha Centauri would take 4 years, 4.3. That's the nearest star to us, Alpha Centauri, 4.3 light years away. So it'll take 4.3 years just to send a message to Alpha Centauri. It takes 4.3 years. So if we could make a wormhole, then we could get there, again, however long it takes to cross that bridge. So wormhole, and this is just another picture of basically the same idea. Wormholes are actually real. There is a real, well, first proposed in 1935, Einstein himself with Nathan Rosen found that wormholes can actually exist. Mathematics supports it. It is possible to drill a hole through 4D space from 3D spot to 3D spot, just like curving a paper and then punching a pencil through from one side to the other. And so the proper name for these things is an Einstein-Rosen bridge. So if you're writing science fiction and you want to sound smarter, you call it an Einstein-Rosen bridge. The first Thor movie did that. Every time they talked about the wormholes that they were making, they called them Einstein-Rosen bridges. If it seems smarter to you, I don't know. Anyway, so they're also called Schwarzschild wormholes because they're based on the math for Schwarzschild black holes, which we're going to talk a little bit more about what that means in a minute. But anyway, they are possible. They actually are possible. There are problems with them. First off, we have no idea how to curve space like this, how much energy it would take, how to drill a hole like this. I don't know. Would you need black holes to do it? If you go into a black hole, you can't come back out again, so maybe don't do that. But you would definitely need to cause an extreme depression into this thing. Furthermore, it was shown a little bit later on in 1962 that you can see it narrows like an hourglass towards the middle. It would actually pinch off in the middle and collapse. And so it would pinch off and each side would collapse back until nothing was left. At the speed of light, it would collapse. So you would have to cross it faster than the speed of light, which again, you can't do. You can't go faster than the speed of light. So you would be unable to cross it before it pinched off and collapsed, unless you could hold it open. And in order to hold it open, you would have to hold it open with exotic mass or negative energy. What is exotic mass and negative energy, you ask? I don't know. Nobody knows. But if we could somehow find something with negative mass, then we could potentially use that to hold open a wormhole. So, again, good for science fiction, unless we actually someday figure out what the heck such a thing would even be. Consider this, though. Return to the idea of the brains, right? That our brain might be next to another brain, like two pieces of a newspaper next to each other in 3D space. Our 3D universe might be next to another 3D universe in 4-dimensional space. And so if you drill a wormhole, or indeed if you even have a black hole, it may end up drilling into the universe next door. So black holes could be gateways to other universes. Black holes, in a way, then, may contain other universes. And actually, that came up briefly in one of the Minute Physics videos earlier in the course, was they mentioned the baby black hole universe idea. Anyway, so if you go into a black hole, you may actually find yourself coming out in another universe. Now, again, can you come out of a black hole? Not in our universe. So if you fall in that sucker, you're not coming back either way. But other universes may have other rules. So I don't know, maybe you would actually fall out in another universe. I wouldn't try it. That seems like a relatively pointless way to die, but if you ever get the chance, I guess it's an interesting way to go. It'll, you'll have an interesting headstone. So yeah, it's probably one way, but black holes could actually be gateways to other universes, and that, for real, that's pretty funky. What about this? What if everything that falls into a black hole comes out of a white hole? Ooh, what the heck is a white hole? I don't know. What do you think? Have we ever observed a white hole? No, there's no such thing as far as we understand. I think we would see it, right? We would see such things if they existed, but we have never seen such a thing as a white hole. So this is an interesting sort of idea, sort of a hypothesis. I wouldn't call it a theory. Theories are supposed to be more substantiated than this, but it's an interesting hypothesis that there could be a white hole, and the math does support it to some extent, but we've never seen anything like it. So it's not really super likely to be a real thing, is it? But who knows? Anyway, maybe if you fall into a black hole, you'll find out you're very lucky and you come flying out a white hole somewhere else. Again, I wouldn't spend your life that way, but hey, if you need to. What about this? Don't forget, we are warping space-time. So a wormhole, therefore, you go to a different place in space and a different place in time. It is actually possible to make a wormhole such that you will come out in the past, creating a closed time-like curve is the proper term for this, where you come out in the past and then you can run around and slap yourself in the face before you went into the wormhole. Good luck with that. So wormholes actually, and most sci-fi movies don't really do this. I guess Avengers sort of did. Most wormholes can actually make a time machine, a true time machine, where you could actually make paradoxes. Physics does not really like paradoxes. A paradox is the idea that something can be true and yet totally not true at the same time. Like something like saying this statement is a lie, and so if something can produce a paradox, then it probably can't really happen. So this is maybe another hint that wormholes can't actually be done. But the math actually support that quantum wormholes are possible, quantum-sized wormholes. So again, Avengers did that for Avengers tapped into that in Avengers Endgame, the best movie of all time. Anyway, so quantum wormholes may actually be possible, which is pretty funky. But scaling them up and creating a true time machine and gateway through space is probably a little bit more than we can really manage. It's neat, though. Pretty neat. Okay, so what we're going to look at now is what are the true properties of a black hole? What properties can a black hole have? We've already talked about mass. So, and I asked this earlier, what is the minimum possible mass for a black hole? Three solar masses, right? Minimum possible mass is 3 solar masses. Is there a maximum possible mass? No. No, there isn't. We have found black holes billions of solar masses, even trillions of solar masses. And we'll talk more about those guys. So are there any other properties that a black hole can have? They're a black hole of information. They don't seem to have a lot of properties aside from just mass. Mass we can measure because of how they deform space-time and because of their effect on other things. Are there any other properties that they could have that we could measure? So first, there are two. There are two other properties. Spoiler alert, there are two other properties. The first one is electric charge. It turns out that a black hole can have electric charge. It could be positive. You could have a positive black hole or a negatively charged black hole. That's a thing that can happen. But let's analyze this and let's think about this. It can have charge, but is it likely to? Let's think about this. So, for starters, if you had a positive black hole, would it attract a positive or be negative charges? As we already just said, opposites attract, right? So if you have a positive black hole, it would attract negative charges, B. Therefore, it would stay positive, become negative over time, or neutralize. And the answer is neutralize. If it were positive, then it would mostly attract negatives until it eventually became zero. And if it continued to eat negatives, then it would become negative. But at that point, it would attract positives to make it back to zero. So no matter what it would do, it would try to neutralize. Okay, so realistically, a charged black hole would try to neutralize, and it would probably happen. Now, you might say, what if there's only negative material to eat? And you have a negative black hole, and its gravitational pull keeps sucking in the negative charges, making it more and more and more negative, right? Well, let's think about that. What's stronger? And this is a question I actually asked once before. What's stronger, gravity or electrostatic repulsion? Electrostatic repulsion is the electric force. It's the fact that negatives will repel negatives. So what's stronger, fundamentally, gravity or electrostatic repulsion? And I mentioned this before, the electric force is way stronger than gravity. Way, 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 way stronger than gravity. Okay, by trillions of trillions of trillions of times. 1,000 trillion, trillion, trillion times stronger, fundamentally, the electric force is than gravity. So if you had a negative black hole, and it was using all its gravitational powers to pull in negative charges, could it? Could it? No, because the electrostatic repulsion would be stronger. So if you had a very negatively charged black hole, I don't care how massive it is, it would probably not be able to eat the negatives. Now, if you had a slightly negatively charged black hole, then sure, it could suck in some more negatives. But it's, oh, I said, I'm not supposed to say suck in. More negatives could fall in. But if it had a substantial charge, then there's no way it would continue to gain that charge, right? Now, anyway, by the way, if you're very familiar with gravity, the gravitational force, right? But you don't normally feel the electric force, right? You're not normally walking by and you're like, oh no, a negative wall, and then you get pulled towards the wall, right? I think we talked about this a little bit before, but why don't we normally get pulled around by electrostatic forces? Have you ever encountered a negative wall? What are things made of? They're made of atoms. And if an atom has 2 protons, how many electrons is it going to have? 2. So generally speaking, everything in the universe is neutral because atoms are neutral because things like to be neutral. So you are generally neutral. Walls are generally neutral. So you don't tend to feel the electric force. If you suddenly lost all the electrons in your body, and so did a wall over there, you would absolutely feel that, all right? Frankly, you felt a little shock every time you lose or gain a little bit of electrons, and you touch a piece of metal, for example, you get a little shock, and you can feel that, right? Oh boy, you can feel that shock. Ouch, dang, right? Surprisingly powerful, even though that's just a relatively small number of electrons moving around. Okay, So anyway, so if you had a charged black hole, it could not continue to gain that charge. Instead, it would inevitably neutralize. If it were negative, it would only pull in positives. And so it would neutralize. Now, what about this? What if you start off with something very charged? I don't know how, again, I don't know how you'd get this, but what if you started off with like a super negatively charged star and then it died? Could it collapse to make a negative black hole? Yes or no? And the answer again is no. It could not collapse. Why could a hugely negatively charged object or a hugely positively charged object, whatever, why could it not collapse in on itself to make a black hole? It's the same sort of answer as a minute ago. Electrostatic repulsion is stronger than gravity by a lot. And so if you have a hugely positively charged object, it would tend to blow itself apart harder than it could pull itself together. It could not collapse. So in other words, you cannot produce a charged black hole by collapse, and you cannot feed a black hole to make it charged. So in other words, you cannot really have a substantially charged black hole. There's no way to get one. You can't birth it and you can't make it. So black holes can have charge, and they may have some small charge, but they're never going to have a very substantial charge. I highly doubt we're ever going to measure the charge on a black hole, because even if it has some, it would be super minor. But theoretically you could, right? Because if it had a charge, then you could hold an electron at some distance and see how the electron moves, right? So you could measure the charge, but I don't think we ever really will. The third property and the final property that a black hole can have is angular momentum. Now, angular momentum we've talked about before. Angular momentum is the idea that that there's conservation of spin. Angular momentum depends on mass, spin speed, v, and the size of the thing, r. Mass times v, speed times r, radius. And angular momentum is a conserved quantity, all right, in space, or anytime you have a closed system. It's a conserved quantity. So for a figure skater, for example, we talked about this a little bit before, right? When she shrinks her radius, her total angular momentum can't change. So if she brings her arms in, shrinks her radius, then her speed has to go up to compensate. And that way, when you multiply mass times speed times radius, you still get the same total angular momentum. It's a conserved quantity. So anyway, there's a question. Shrinking object spins A faster or B slower? A shrinking object, as you can see in the picture, spins faster. Now, you can see this happen if you watch a figure skater bring her arms in. You can see it. And that's just bringing her arms in. That's not a huge change. Now imagine a collapsing star core, collapsing all the way to 0 size. That's going to spin faster, right? A black hole is the ultimate shrunken object, and oh yeah, it'll spin a lot faster. This, frankly, is the exact same thing we talked about with neutron stars, that they will spin faster and faster and faster as they collapse, smaller and smaller and smaller. And that's how you get, a neutron star that can spin in seconds or milliseconds. From something like a star, our sun spins in a month. But a black hole collapses even more than a neutron star. So it is going to be spinning pretty fast. So how could you measure this? Well, it turns out that when something is spinning in space-time, it doesn't just curve the space-time it's in, it will actually drag it with it. This is called frame dragging. Frame dragging. It drags its frame of reference along with it. So it's a little bit like putting a spoon into let's say dough or something, and then turning the spoon. You're going to drag the dough with you, right? You're going to drag the dough and spin it. So and this is something that happens. We have measured the effect of frame dragging, for example, from the Earth. Just the Earth does it. The Earth spins in curved space-time, and as it spins, it drags the frame with it. So what we did is we launched a little a satellite. And again, this does not happen according to Newton's gravity, but according to general relativity, Einstein's gravity, it does. So for example, we launched Gravity Probe B, which was a really cool mission, which had a little gyroscope in it. And what we saw over time was that the gyroscope was actually twisting around. This actually is one of the things that leads to precession, is you've got a spinning object on a twisting surface, and so it ends up precessing. So frame dragging is a thing that happens, and if that happens from the Earth in a measurable way, you better believe it's going to happen around a black hole. So what does this mean for a black hole? It's pretty neat. So if you have a black hole that is rotating, then the math is a little bit more complicated. And we call that mathematical model, we name it after Kerr, the guy who first calculated it. So a Kerr black hole is a black hole that is rotating. It has angular momentum. It has mass and angular momentum. So because it has mass, it has an event horizon, which we already talked about. But because it has angular momentum, there's another boundary called the ergosphere. And the ergosphere is a really, really interesting one. All right. Within the event horizon, light cannot escape because the escape speed is too high. Within the ergosphere, and you can see the ergosphere is not really a sphere, it's like a flattened sort of shape. So it's actually the same as the event horizon at the poles, but around the equator, the ergosphere bulges out. Within the ergosphere, everything must move with the rotation of the black hole. If the black hole is rotating clockwise, everything in the ergosphere has to rotate clockwise. Now that may not sound quite as dramatic as the event horizon does, but it's pretty interesting. So let me try and walk through this with you. So here we have the black hole. That's the event horizon right there, all right? But the boundary of the ergosphere is this green area, all right? That's the ergosphere. This is a black hole that's rotating counterclockwise. And so anything going into the ergosphere, by the time it's in the ergosphere, has to be moving counterclockwise, has to. So notice the green path here. This is an object that falls towards the black hole, and it falls, and as it moves in and it falls and spirals in, of course it ends up going counterclockwise. That's fine. But now look at the blue line. This sucker is fired in on a straight shot straight towards the black hole. But that's not okay, because in the ergosphere, it has to be going counterclockwise. So even though it is actually 1 in a million fired on a straight shot straight at the black hole, it should go straight in, that's not possible. Within the ergosphere, it has to turn counterclockwise, and so it does. Instead of going straight, it'll actually bend around and be dragged by the rotation of space-time underneath it. It will be dragged until it is going counterclockwise. Now check out the purple lines. This is where it gets really dramatic. This purple line should end up coming in over the top of the black hole and end up coming in clockwise. But that's, again, not allowed. So as space-time twists it, right? Imagine digging your fingers into this and twisting it counterclockwise. As space-time twists it, this pink curve actually comes in, and then, yes, it goes in going around counterclockwise. Same with this pink curve. Same with this pink curve. Now check this one out. This last pink curve is the most dramatic. This sucker is going to go in. It's just grazing the ergosphere. It may actually escape, right? It's just going to graze the ergosphere and then keep going around. But because it passes inside the ergosphere, it cannot go it cannot go clockwise. Like this, it's moving on a clockwise path. That's not allowed. And so it straight up pulls a U-turn, right? Check that out. It actually pulls a U-turn. And as soon as it hits the ergosphere, it's going counterclockwise now. The red curve misses the ergosphere entirely, and so it can just go by clockwise. But this pink one actually has to do a U-turn in order to ensure that within the ergosphere, it is going the same direction as the black hole. I think that's pretty amazing. It would look pretty funky to see that, right? To see what that would look like if you could actually see it, which is pretty wild. So the event horizon is, I think, a little bit more understandable, a little bit more obviously impressive, but the ergosphere can be pretty impressive as well. Okay, so that's it. Black holes have 3 properties that we could measure. That's it. They've got mass, angular momentum, and charge. That's it. There is no other information whatsoever that you can get from a black hole. So they are devoid of any other information coming out. That's it. And so this was given the really awkward name of the no-hair theorem. Probably the weirdest name I've ever heard, the no-hair theorem, because I guess black holes are like bald of information. There's nothing else coming out from the scalp of the black hole. I guess this is so weird. You can tell that whoever came up with this name was probably balding, right? Because when you're balding, and believe me, I'm thinning up top too, you know, man, it hurts. But when you're balding, there's nothing else you can think about. So I'm sure whoever came up with this was absolutely going bald. And so they were like, oh, there's no other information you can get. There's nothing up there. Oh, it's the no. Anyway, so John Wheeler apparently was the guy who sort of coined this. He said black holes have no hair. I'm not going to do it, but feel free. Google image search John Wheeler. You tell me if he's bald. Anyway, so, but the idea is that's it. That's all you can gain out of a black hole is mass, angular momentum, and charge. And charge, you probably will never measure. So really, it's just mass and angular momentum, right? What is in there, we'll never know. Is it matter, antimatter, magnetic, nothing. There's no information except mass and angular momentum and theoretically charge. The no-hair theorem. Shave your black holes. Okay, so anyway, that sounded terrible. I'm never going to say that again. Anyway, so the mathematics to describe these objects, I already sort of mentioned. The basic black hole that just has a mass, it's not rotating, it has no charge. The basic black hole that just has mass was computed first off by this dude Schwarzschild. So those are called Schwarzschild black holes. If you want to describe mathematically a black hole that does have mass and it is rotating, that would be a Kerr black hole. If you want to add in charge, but not rotation, then that mathematical model was made by Reisner and Nordstrom. So it's called a Reisner-Nordstrom mathematical model for a black hole. The most complicated possible model for a black hole would be rotating with mass. All these have mass. Rotating with mass and charge. That would be the Kerr-Newman. Why do you care about the names of mathematical models? You don't. Does it really matter? No. Realistically, any black hole in nature will be a Kerr-Newman black hole because they will have some rotation. They will have mass, obviously, and they will probably have some level of charge, albeit not much. But, well, I suppose you do care slightly about the names of different mathematical models because I will ask about them on the test. Haha. So, yeah. But, yeah. So anyway, there's different mathematical models for black holes. As we've already established, probably none of these are totally accurate because we can't get it to work with quantum mechanics yet. But, hey, we'll get there. What's your last name? Maybe eventually we'll come up with a better model, and it can be the Einstein U black hole. I don't know. Get going. Now, what about entering a black hole? That's our next question. What would it look like to enter a black hole? And now we're going to bring in a whole lot more interesting properties. We're going to talk about, again, as we've already sort of mentioned, time changes. Time ticks slower near a black hole. It's called time dilation. We're going to talk about gravitational reddening that you can sort of see happening in the image. We're going to talk about the tidal effects that will ultimately rip you to pieces. And we'll talk about some other features of a black hole, like the photon sphere and more. So entering a black hole is our next step on this journey. So to begin with, let's talk about time dilation. And first, before we get to the time dilation around a black hole, there are two types of time dilation: special relativity, which you might have heard about more before, and general relativity's time dilation. And they are different, but they both do matter, and both are going to come up repeatedly in this course. So first, let's talk about special relativity, because again, you may have heard about it in 181. Special relativity is the idea that as you go fast, as you get close to the speed of light, time will slow down for you. Time will tick faster. So if you have someone stay home, living at normal time, and someone head out on a rocket ship, or better yet, some more advanced spaceship, going at, let's say, 99% the speed of light, then by the time the person going at 99% the speed of light has returned, it could have been years on Earth, but it may have only been days or months. for the person on the spaceship. Time ticks slower when you are moving at very high speed. So, so if you could look in the window of a passing spaceship moving close to the speed of light, you would see the people on board moving in slow motion. Now, do they feel like they're in slow motion? No. This is a relativity thing. Time is actually passing differently in these two frames of reference. On Earth, or at normal speeds, I suppose, time will pass one way. But if you are moving closer to the speed of light, time will pass slower. You don't notice that, okay? For you on board the spaceship, and this is where it gets really weird, for you on board the spaceship, time is passing totally normally. You look around, you have a cup of coffee, you know, go to the washroom, whatever you got to do, but time is totally normal. And actually, when you look out the window at planet Earth as you pass it by, from your perspective, it's planet Earth that's moving really fast. And so it's planet Earth that is experiencing the slow time. So it gets kind of weird. Anyway, so that's time dilation, that time slows down as you move closer and closer to the speed of light. General relativity has its own time dilation. So there's two types, the special and general. Special relativity is something Einstein came up with in 1905. General relativity came up with in 1915. So it took him a little while to come up with two totally revolutionary concepts. You can remember the difference this way. Special for speed. As you get closer to the speed of light is where special becomes important, whereas general relativity, general G for gravity. Okay, so keep them separate in your head. We've got special for speed and general for gravity. So according to general relativity, as we've already noticed from that rotating cube animation, time passes slower when you're near a source of gravity. So that includes Earth. When you're closer to Earth, we are fairly close to Earth right now. But if you look at two different altitudes even, so for example, Boulder, Colorado is at higher altitude. So it doesn't seem right, but it's true that it's farther from the Earth, sort of, by a little bit. Nonetheless, Greenwich, England, at a lower altitude is closer to the Earth, even though they're both, yes, on the ground. But Greenwich, England is closer to the center of the Earth. And so Greenwich has stronger gravity, slightly, but that is enough to slow its time just a little bit. Okay, the stronger gravity gets, the slower time goes. And so time will actually tick a little bit slower in England than it will in Boulder, Colorado. Now, this is not a strong effect. You would never in your life notice a single second of difference between these two locations. But just because you can't notice it doesn't mean you can't measure it. And with super accurate atomic clocks down to the nanosecond, you absolutely can see the difference, that time is actually ticking slower in Greenwich, England. Now, if you go further, then you can more easily see the difference. So for a greater difference, so for example, we are obviously fairly close to the Earth. We're on the ground at whatever altitude we're at in Toronto. Satellites in space are much farther from the ground than we are, much farther from Earth. You could push it farther, of course, but satellites are farther from the Earth than we are. So from our perspective, right, look from Greenwich to England, from Greenwich to Boulder. From our perspective on the ground, satellites in space will experience fast time. From the satellite's perspective, we are experiencing slow time. But either way, there is a difference there, and clocks will tick differently on the ground versus in a satellite. And definitely near a black hole is an extremely high gravity environment, and high gravity slows time. So, or let's say powerful gravity slows time. So definitely near a black hole, time will tick very, very, very slow. And this will get pretty weird. So, and again, note this is totally different from special relativity, where when you get close to the speed of light, time slows down. Here, it's when you get close to a source of gravity, time slows down. They are both types of time dilation, ways to stretch out time, but one has to do with speed and the other has to do with gravity, right? And they are not related things, not really. So this is a problem for satellites. Our satellites in space, for example, GPS satellites. Have you ever used GPS? Because you have. This may seem like a very okay, sure, I guess maybe that might happen, but it doesn't matter. It doesn't affect me. It does. If you've ever used GPS, this has affected you because GPS satellites are just clocks. And if the time is wrong, then they won't work. So GPS satellites have to contend with two things: the fact that they are farther from the Earth than we are, so they are experiencing faster time than we are, or in other words, we're experiencing slower time than they are. So they're experiencing fast time because they're farther from the Earth, but they're also moving fairly fast. Not super incredibly fast, but slightly, they're moving pretty fast. They orbit the Earth, multiple times per hour even. And so, I mean, I don't know what the average orbital rate is. I think the space station goes around in about 40 minutes. So anyway, whatever it is, though, they're moving pretty quick. So because they're moving at high speed, they actually have slowed down time because of special relativity, sped up time because of general relativity. Either way, their time is pretty messed up, and we have to take that into account. So here's a little video from Minute Physics talking about exactly that, talking about the GPS system that we've all used to give direction, and how if you don't account for these time variations, it simply won't work. So check it out. And then there's the link in the top right, and then come on right back. Okie dokie. So yeah, so there you go. So GPS satellites actually need to use both, right? So let's just review that quick. According to special relativity, time passes A, slower at high speed, B, faster at high speed, C, slower at high altitude, or D, faster at high altitude. So special for speed, so it's A or B, and the idea is that as you get to high speed, time will slow down. So the answer is A. Now, if I change it around according to general relativity, what will it be? So then we're dealing with altitude, and at high altitude, and don't get tricked around right? So we are at low altitude, and so we are experiencing slow time because we're close to the source of gravity. If you get to high altitude, then it'll be fast time. Okay, so the answer there would be D. Faster for satellites than for us. Around a black hole, you're closer to the source of gravity. That would be slowed down time for sure. Right? For real satellites, combining both effects, and the video mentioned this, combining both effects, time passes A, slower, or B, faster. So the video mentioned that for real satellites, the general relativity effect is more important than the special relativity effect. You do have to calculate both of them, but the answer is B, faster. So general relativity wins out, is what the video said. That time will move faster, mostly because of general relativity, whereas special relativity doesn't have a huge impact. That's because the satellites simply aren't moving that fast, right? General relativity will have a higher impact at that speed. I think it's funny that the engineers sent it up uncorrected because they didn't believe that relativity could be true. So the moral of the story is engineers are just not very smart. Yeah, sorry, but it's true. It's not true. Please don't take that too seriously. Okay, anyway, moving on. Gravitational time dilation is obviously going to be more substantial around a black hole. That's the strongest possible version of this as you get to infinite gravitational pull. But you do have to get close enough, again, at whatever distance from a black hole. Don't forget, right? These things are not magic. Now, you can be incredibly far from a black hole and have almost no gravity at all. They don't suck you in, right? So let's not over dramatize these things. But if you get very close, then yes, time will slow down dramatically. So let's imagine a scenario where you are in a spaceship and your friend is in a different spaceship and you're going to explore a black hole. And you park yourself in a safe, stable orbit, whereas your friend is a thrill seeker and probably an idiot, and decide if you have, my friends are idiots, so you probably, anyway, so your idiot friend decides to get closer and closer and closer to the event horizon. What would happen in this scenario? So again, time slows down near a black hole as compared to farther from it. So close to the black hole, maybe only 15 minutes pass, whereas hours go by, potentially, farther from the black hole, right? Time is slowing down close to the black hole. So you will watch your friend through the window of the spaceship moving in slow motion. Would you notice this on your spaceship as you get closer to the black hole? Again, similar question I asked before. Would you notice time slowing down for you? No, this is a relativity thing. It's about comparing to different places in the universe or to different situations. Everything's relative, but nothing is, life is normal for you on board your ship. It's only weird when you look outside. Now, here's where it gets extra funky. This gets more and more strong as you get closer and closer to the event horizon. And you can see, I can't remember what these two lines are different for, but anyway, they're measures of time dilation, and they are both asymptotic as you get closer to 1 Schwarzschild radius. So here we go, starting from 10 Schwarzschild radius, and let's, I guess, look at the red line. At 10 Schwarzschild radii, which is pretty close to a black hole, like that's closer than I'd ever want to be, but you're still at 90% normal time. That's not too different. At 2 Schwarzschild radii, you're at about 40% normal time. Time is getting very slow, dramatically now. Right, 4 days for your friend out there is experiencing 10. But then as you get closer and closer and closer to the event horizon, this goes asymptotically to 0 relative time. In other words, as you approach the event horizon and get closer and closer to 1 Schwarzschild radius, time slows down, and stops at the event horizon. So your friend falling into the black hole, time stops for him and he freezes completely at the event horizon. And from your perspective, he never actually enters. So this might be one of the weirder things I tell you through this whole class today. Nothing from our perspective ever enters a black hole at all. It simply freezes at the event horizon. Yeah, mull on that one. Nothing actually goes in. Okay, now this is a relativity thing, right? So your friend, your idiot friend, he's near the black hole. So he sees you moving A, fast, or B, slow. So if you see him moving in slow motion, he sees you running around like the Flash out there. So you are moving very fast from his perspective. All right, you're in the low gravity area, and so you are experiencing faster time. No one can agree on whose clock is correct because they are both correct. Both clocks are correct. There is no true time. All right, both clocks are correct, and it just depends where you're talking about it. Now, the next thing that we're going to look at is the redshift. All right, now redshift is a term you've heard before, red and blue shift, with regards to the Doppler effect. This is not going to be due to the Doppler effect. For a black hole, you have what's called gravitational redshift. But first, let's review Doppler redshift, just so that we're clear on what we mean by this. So when a source of waves is moving, then as it moves, for example, to the right, you can see the waves it's emitting ahead of it get compacted. Lower wavelength means higher frequency, means it'll look slightly bluer than if the waves were emitted normally. So this is the normal wavelength, normal frequency. This is a higher wavelength, lower frequency light or sound or whatever. And so it'll look bluer. Even if it's not blue, it doesn't have to be blue, but it'll be bluer. Blue is the high frequency side of the spectrum, blue and violet, right? So something moving towards you will appear to have smaller wavelengths, higher frequencies. It'll be what we call blue shifted. Whereas something moving away from you, as it moves away from you, it's moving away from the waves it's emitting towards you. It ends up stretching them out. And that stretched out wave has a higher wavelength, lower frequency, shifted more to the red side of the spectrum. It doesn't have to be red, but it'll be shifted to the red side. So this is called a red shift. All right? Hopefully you remember this because this is fairly important in 181 and will be again important. So this happens for sound, it happens for light. If something's moving towards you, it looks blue shifted. If something's moving towards you, it looks red shifted. This does not mean that the thing will look blue again. It doesn't even mean the thing will look bluer. It just means it's shifted to the bluer end of the spectrum. Right? You normally will not see a color shift. Something has to be moving at like a decent fraction of the speed of light for you to see any actual color change. But what you can definitely measure, and you did this calculation in 181, what you can do is you can look at the lines in the spectrum. Those are very sharp and very accurate, those absorption lines from different elements emitting the light. And those absorption lines will shift back and forth to the blue or to the red, depending on motion. So you can actually very directly and clearly measure the blue and red shift of something which tells you its speed towards or away from you, or radial velocity towards or away from you, based on the changes in the wavelength of those lines. So that's the Doppler effect. Doppler gives us a red and blue shift based on the way waves are compacted or stretched ahead or behind the emitter. General relativity also gives us a type of this. Gravitational redshift is not related to Doppler. Okay, so that's why I wanted to explain Doppler first, because I want you to be clear on what we're talking about. Doppler is one thing and it's important. Gravitational redshift is a totally separate type of redshift. It's not related to Doppler at all. Instead, what happens with gravitational redshift is that, well, it's hard to move away from a black hole. Understatement of the class. It's hard to move away from a black hole. So as light is moving away from a black hole, not from within the event horizon, that's impossible. But if it's starting from well outside the event horizon, that's fine, that's escapable. As the light moves away, it will get stretched out. It will lose energy, all right? And as it loses energy, that means it's going to the lower end, lower frequency end of the spectrum, that's redder. So it will redshift. Light leaving the vicinity of a black hole is redshifted as the energy drops, as it loses energy, crawling away from this black hole. It's very hard to do, right? So any light leaving the vicinity of a black hole, again, not from within the event horizon, that's impossible. But anything outside the event horizon, you can see. As the light leaves from outside the event horizon, it will lose energy and be redshifted. This is not related to Doppler. This is gravitational redshift. So for example, if you have a robot probe parked, 10 kilometers away from a 3 kilometer Schwarzschild black hole, and that robot probe has a blinking light on it, sending out visible light. For you to see that light, you would have to turn on a radio if you're out here. You would pick up the appearance of the probe using a radio, which is pretty odd. So what if you wanted to see a light from the probe? It would have to emit X-rays. If the robot probe sends out X-rays towards you out at 10,000 kilometers, if the robot probe sends out X-rays, those will lose energy so dramatically that by the time they reach you, it would be visible light. You would be seeing what was emitted as X-rays, which is the only real example of X-ray vision I can think of. So this was actually measured for the very first time in practice from a black hole a couple of years ago. So a star, S2, flew by the Milky Way's supermassive black hole, Sagittarius A star, at 3% the speed of light in 2018. And when it did, there was a strong Doppler effect, but there was also a change in frequency beyond that attributed to gravitational redshift. And so we actually have measured the gravitational redshift effect from a star orbiting or passing by a supermassive black hole, which is pretty cool. That was some really impressive work. Now, again, this is a relativity thing. So if leaving the vicinity of a black hole is redshifted, right? So anything near a black hole will look redder than it otherwise would. Even if it looks blue or whatever, it looks redder than it otherwise would look, lower energy than it otherwise would look. Within the ship, of course, this is a relativity thing. Within your ship, you're not looking at yourself saying, oh my, I'm looking quite red today. No, you look totally normal within the ship. The far off ship will see the approaching ship. So you in your safe ship will see your idiot friend approaching, become A, redder or B, bluer? Redder. And your idiot friend looking at you, what are they going to see? They're going to see you. Light falling towards the black hole, conversely, will gain energy, which it should not be a surprise. Light falling towards a black hole gains energy. Sounds like a fairly obvious statement to me. So any light moving towards the black hole, and your idiot friend is towards the black hole, so light moving from you to them will gain energy, so you'll look bluer to them. Everything in the outside universe will look higher energy to them, all right? So actually, if we go back here for a sec, that means that any starlight falling towards that probe will strike it in the form of X-ray radiation, right? Because look at this, backtrack this. Visible light falling from out here falling towards the robot probe, visible light will strike the robot probe as X-ray radiation. Another good reason not to park your ass near a black hole is every light that you could normally see will instead be striking you in the form of dangerous high-energy radiation. So the approaching ship sees the far-off ship become bluer. This is a relativity thing, depends which one you're talking about. Now, what happens next? What if your friend jumps from the ship and dives into the black hole, right? And that guy really is an idiot. Anyway, what if they do it? What if they jump from the ship and dive into the black hole? Can they fall on in? Can they experience the singularity for themselves? What will happen next? So what will happen next for them has to do with tidal forces. Tidal forces are pretty fundamental in physics. Most people don't really understand them very well. Here's a fairly basic question for you. Why does the Earth have tides? Everyone knows what tides are, right? Tides go in, tides come out. Easy enough to explain, right? But can you? Why does the Earth have tides? So this is when the water level drops and rises. And most people know it has to do with the gravity of the moon. So imagine then the moon is directly overhead right now. In Toronto, we never have the moon directly overhead. But imagine the moon is directly overhead and we are standing, I don't know, in Lake Ontario at the moment. Where would we have high tide or low tide? Or medium? What you would think is that the side of the world with the moon overhead would have high tide, and the other side of the world would have low tide, right? That the waters would be pulled upwards towards the moon on the side of the world with the moon overhead, and on the far side of the world, where the moon is essentially underfoot, you would expect the water to be pulled down to the ground, right? That's not what happens. So we have tidal effects. It's not just the gravity of the moon. Okay, when I ask a test question about this, it's going to read a little bit tricky. There's a key word here. It's not just the gravitational pull from the moon. If it were just the gravitational pull from the moon, then this area of the world would be pulled towards the moon. The land is pulled as well, but you don't notice it as much. The water would be pulled more, so you get a bulge. The water level rises off the ground here, and you would expect that the water would fall here, but it doesn't. Notice that the water level rises on the near side and the far side of the world equally, totally equally. This is symmetrical. So what's going on here? What's happening is it's not the gravity of the moon that pulls the water up. It is the difference in the gravity of the moon across the world. Okay, so we got to compare it. It's a comparative. It's a differential force. That's the key word. It's a differential force. In order to see the effect of it, you have to compare the difference in gravity at two different points. So if we compare the difference in gravity from here, the side closest to the moon, don't forget that gravity decreases with distance, right? So this spot has a higher level of gravity than the middle of the world does. And so this spot is being pulled harder than the middle of the world. And so this spot is being pulled away from the middle of the world. And so this spot rises. The water moves more than the land by far, and so the water bulges upwards towards the moon, creating high tide. But what about the far side? It's actually the exact same thing. I mean, it's the exact same thing mathematically, but it doesn't look like it, but it is. So now let's compare the middle of the world to the far side. The middle of the world is experiencing stronger gravity than the far side, because again, gravity diminishes as you get farther from the moon. So the middle of the world is experiencing stronger gravity than the far side. And so in this case, it's actually the middle of the world being pulled away from the backside. The effect of this is that the ocean floor is being pulled away from the ocean top, right? So here's the surface of the ocean, here's the ocean floor. The ocean floor is being pulled away from the ocean surface, creating a stretch, making the ocean rise away from the ocean floor. It's more that the ocean floor is moving away from the ocean surface, but it doesn't matter. It's the exact same effect. The effect is the ocean is higher here, and it's higher here than it otherwise would be. Now, perpendicular from that, notice what's going on over here and over here, okay? It's not nothing. It's not just the water is being pulled away. This side and this side are being actively compressed, because notice that this area of the world is being pulled towards the moon, which means being pulled to the right and somewhat up in this picture, and this side of the world is being pulled towards the moon and somewhat down. So the Earth is actively being squeezed towards its center. And that's what we see in the bottom picture here. Relative to the center of the Earth, that's this picture. So if we take everything relative to the center of the Earth, this side is being moved away from the center of the Earth. This side on the left is being moved away from the center of the Earth. And the top and bottom are being moved towards the center of the Earth. We're looking down on the North Pole here. The effect is that over here at the top and bottom of the picture, we get low tide, where the ocean is being actively squished. And at the left and right, we get high tide, where the ocean is being actively stretched. This is a tidal force. It's the differential force as gravity varies across the Earth. So imagine taking the thick elastic band and stretching it. Hold one side in your left hand and the other side in your right hand, and then stretch it with your right hand. Keep your left hand still. Does it only stretch on the right side of the elastic? Or does it stretch the whole way along the elastic? It stretches the whole way along the elastic, right? It's symmetrical. The stretch will be on both sides of the elastic, just like the stretch here. And this is what it is. It's a stretch. The stretch of the Earth will be on both sides equally. And if you stretch an elastic band, you'll also notice the same thinning in the middle as it gets sort of contracted in the middle and stretched out to the sides. So that's the tidal effect of the moon on the Earth. All right. So, I went backwards. So this is a differential force again, and this is why we have 2 high tides per day. One when the moon is relatively overhead, and one when the moon is relatively underfoot. Okay, Earth is pulled apart and squeezed. So don't forget, of course, we are rotating. So us in Toronto, we have high tide now, and then 12 hours later, high tide. Okay, so every day we have we have high tide in the morning, and then again high tide 12 hours later in the evening. All right, 6 a.m., 6 p.m., high tide. If you were a fisherman, of course, in the Atlantic, you would probably know this, but if you've lived in Toronto your whole life, you may not really know much about the tide. Anyway, that's how it works. You get high tide twice a day and low tide in between. And that's why. And that's from the moon pulling on the Earth. And the moon is pretty small compared to the Earth. It's a quarter of the diameter. Pretty small compared to the Earth, but it still has an impact. Now imagine you getting close to a black hole. As you get closer to the black hole, let's say you're falling in feet first, or rather, let's be courteous and say it's not you, it's your idiot friend. As your friend falls towards the black hole feet first, gravity is stronger at his feet than it is at his core. So his feet will be getting pulled away from his core, and his legs will get stretched out. Meanwhile, his head is being pulled weaker than his core is. His core is being pulled harder than his head. So his core will be pulled away from his head, which again will make for a stretch in the top half of his body. The effect will be a little bit like the medieval torture implement, the rack, where he will be stretched top to bottom, and don't forget the squeezing perpendicular to that. All right, he will be stretched vertically, squeezed horizontally in a process called spaghettification. It's a funny sounding word, spaghettification, but it's a real word, and it's the best word, okay, in the English language, spaghettification. Oops, I keep going backwards. So again, the torso is pulled harder than the head, so it'll be pulled away from his head, causing a stretch. Feet pulled harder than the torso. It's the difference in gravity across his body that'll get him. His feet will be pulled off his body, and his body will be pulled off his head. He will be stretched, squeezed, and torn apart. This is not a relativity thing. This is a brutality thing, all right? If the moon is strong enough to raise the oceans off our planet, imagine what a stellar mass or supermassive black hole can do to your body. You will be stretched and squeezed until you are turned into a noodle. And this will be absolutely brutal to see. This is not a relativity thing. Again, okay, it's called spaghettification. It sounds funny. It's not. It'll be horrifying. There's even going to be some red sauce. Okay, yeah, it's going to be nice to watch. Don't watch. You would not want to watch this. It would be absolutely horrifying, and this would be the most brutal way a human being could be murdered that I can possibly think of. It'll be horrific to watch, and this is not relativity. Your friend will be killed by this. It depends on the size of the black hole where he will be killed by this, but it is inevitable. Before striking the singularity, you will be killed by this. There's no avoiding it. This is millions of times stronger than the moon Earth tidal forces. It will rip your body to atoms. So yeah, you'll be spaghettified, thinner than a spaghetti noodle, and yeah, that'll be red. So depending on the size of the black hole, you can actually make it through the event horizon. So for example, a supermassive black hole is much more spread out. And so you can make it inside the event horizon before being spaghettified. So, for example, in Interstellar, where they have an extremely accurate representation of a black hole, and Matthew McConaughey goes flying into the event horizon, at which point everything gets super weird, but you might pause the movie and say, oh, shouldn't he have been spaghettified? No, because they are careful to say in the movie that it is a supermassive black hole, and so the spaghettification does not reach fatal levels until you're well inside the event horizon in that case, because it's so spread out. It's such a big thing that you have to get a lot closer to the singularity before it really rips you to shreds. So what do you see as your idiot friend falls into the black hole? He will slow down, slow until he eventually freezes. He will gravitationally redden, eventually shifting out of the visible part of the spectrum. And then the real reddening will kick in too, as he is stretched, squeezed, and torn to shreds by spaghettification's tidal effects. And that'll be what kills him. What does he see before he dies? You are moving around incredibly fast and looking blue. And then the world goes dark as he is torn to shreds. Goodbye, friend. I hope you weren't a good friend. What about this? What about lensing, right? Don't forget the lensing. So here we have an artist's impression. So if you are looking at a black hole, you can look around the black hole. As your friend gets close to it, you can actually, for example, if you look close to a black hole, well, it doesn't look like much, it's black. But if you could somehow paint grid lines on the thing, just like lines of longitude and latitude that we would imaginarily paint on a globe of the world, you could actually see every grid line from any side of the black hole. As you look straight at it, you can see the back side. You're looking at the front side right here. The back of the black hole would be right here, painted around the edge. And then actually light can wrap around multiple times before coming to you. And so you'll actually see the front side, then the back side around that, then the front side around that, the back side around that. It gets really, really weird just how light can be warped by this situation, as we'll see in a little video in a bit. But what would it look like then, from your perspective, if you were to fall into a black hole? What would the lensing be like for you? So again, you can actually see the back. So here we have a black hole with lines of longitude and latitude drawn on. That is the true north pole of the black hole. That's the true south pole of the black hole. And it is so distorted that you can see both of them on the front face, and the back of the black hole is around that. And then the lines get really messed up towards the edge because you can also see the front around that and the back around that and then the front around that, and it gets really, really weird. So what we're going to do now is we're going to watch a video of this, and it's going to go fairly quick. I think it's like 30 seconds. You can see down here, we're going to follow the trajectory in as we go through various regions, and the red line is the event horizon. When you pass through the event horizon, then things get extra weird. So here's our little video of this. This goes fairly quick. What we're going to do right after this, we're going to watch this, And then we're going to watch a longer version of it that actually bothers to explain what the heck we're seeing. But there's the link in the top right. Check it out. Okay, so what the heck was that? What just happened? So what happened is, as you fall through the event horizon, it actually breaks in two in a way, because there is always an event horizon ahead of you, but there's also the event horizon sort of behind you. It gets weird, and the view of the universe becomes super distorted. So for an explanation of that, we're going to watch this, A Journey into a Black Hole, and this is a slightly longer video that will explain step by step. Most of it we've already sort of talked about, but let's take a longer look at what just happened. So there's the link in the top right. Go check it out. Okay, so there you go. That's our explanation for a little bit of what we saw in that video. Now, this video, A Journey into a Black Hole, mentioned a lot of like orbits and what's stable and unstable, and it gets a little confusing, I'll admit. We're not going to worry too much about that. Most of the important stuff from that video was stuff we'd already talked about. There were only a couple elements that we hadn't talked about at all, like the idea of the photon sphere, where light can actually orbit, because that's the right speed for light to actually orbit a black hole. That's an interesting point, where you can look straight ahead and see your backside, right? Because light's going from your back all the way around to your front, which is pretty funky. So you can actually see you ahead of you, which is weird. So that point, the photon sphere, that's one of the few that we hadn't really talked about. The photon sphere is at about 1.5 Schwarzschild radii. Light at this distance can actually orbit the black hole. That's the only way it can stay there stably. And you can actually have a stable orbit there, but it would require infinite energy. As the thing said, orbits there tend to degrade. So you would need to be having infinite energy output in order to stay in orbit there, assuming you had mass, so that's not really doable. But yeah, as a result, there is an inner edge to any accretion disk. Okay, as the video sort of mentioned, there is an inner stable orbit, which is going to be an edge to the accretion disk, and you can't get any closer than that. So as an accretion disk is feeding a black hole, that's where matter will fall right on in. It can no longer orbit and spiral in slowly due to friction. Instead, it will just fall more or less directly in. Not straight line, but it'll fall right in. So black holes can feed, of course. Anything getting close adds to a black hole. So here we see the formation of an accretion disk from a dying star. This is the most accurate animation. And we see a jet output there. We're going to have to talk more about that. Down here, this is a more accurate animation showing true gravitational lensing from a binary black hole system. This is a computer simulation down here from, what's it called? Extreme Spacetimes. You can look up their website. They have a lot more really, really cool animations. Extreme Spacetimes. And what's amazing about this is there's actually right there, when the little black hole is in front of the other one, and vice versa, there's actually a moment where light is coming to us from in front of the big one, right? Like light right there. Light has to be doing some weird figure-8 path around the back one and then around the front one in order to come to our eyes, right? So you get some really weird effects. Anyway, so black holes can grow. We can see black holes feeding with accretion disks. And we have indeed observed black hole mergers, which is what we're seeing down here. There's nothing to see when that happens, unless you could actually see the lensing, as in this animation, but we can't. Or at least we haven't yet seen lensing around something so small. But what we have done is, over the last few years, we've started to detect gravitational waves. And when black holes collide like this, that produces an extremely strong gravitational wave signature. And most of the gravitational waves that we've detected so far have been from black hole mergers, with like 20, 30 solar mass black holes colliding and turning some of their energy, like several solar masses worth of mass, into pure energy in the form of huge gravitational waves that stretch and squeeze the Earth, and so we can actually pick them up, which is pretty amazing. So how have we detected black holes? Because they are real, right? We have detected black holes. They are real. We don't get Hawking radiation. Keep that in mind. Hawking radiation is theoretically emitted around the edge of a black hole, not from inside the event horizon, but around the edge. Hawking radiation should be emitted. But we've never picked up Hawking radiation yet. However, we can see them because of their effects on the rest of the universe, right? We can see their gravity. We can see what they do. So there was a study that found a black hole in a triple star system. It turned out, we thought it was a double star system, and it turned out that there was actually a black hole in that system because the innermost star was actually orbiting a black hole. So that double star system turned out to be a triple star system. I can't remember the name offhand, but that was a pretty interesting system where we confirmed a black hole existed, because we can actually see, even with the naked eye, you can see those stars, but you couldn't see the black hole. But it was there because we could see them orbiting. And for example, there is a black hole at the heart of the Milky Way that we have confirmed in this way. So here we see an animation of the stars at the center of the Milky Way. And this is, what is this, about a decade worth of footage? I could probably find a newer GIF, I suppose. But anyway, about a decade worth of footage of infrared. And that's real data. This is real data. You're looking at real stars as they orbit. Nothing. Right there at the crosshairs, that's the center, or that's the focus of their orbits. And there's nothing there, but that's what they're orbiting. Now, when you can track an orbit like this, what you can do, and Kepler did this 400 years ago. We use Kepler's laws to do this. 400-year-old equations tell us how to do this. You can measure the size of the orbit and the speed of the orbit and use that to figure out the central mass. So as we watch these stars, we figured out that they are orbiting something that is 4 million solar masses. But it's invisible. There's nothing there. There's no heat. There's no light. There's nothing at the crosshairs. There's only one thing it can be, 4 million solar masses. And that's a black hole. It's a supermassive black hole. And for all that it's massive, it is, don't forget, tiny. Smaller than the solar system. So the stars can easily orbit it. They're not hitting it. Right? By the way, will this black hole eventually suck in the galaxy? Will it? I mean, you're looking at stars orbiting it, aren't you? Right? People think black holes suck things in. No, you can totally orbit a black hole. It's totally fine, unless you get too close, and then orbits will degrade. But no, these stars are orbiting that thing. And frankly, for the matter, don't forget that our galaxy is incredibly big. Our galaxy is, hundreds of billions of solar masses. So 4 million solar masses in a black hole, that sounds like a lot, but that's nothing. If that black hole were to disappear from the center of our galaxy completely, nothing would change. Nothing. It wouldn't matter. These stars, I suppose, these particular stars that we're looking at, they'd go flying. But that's about it. All right. So again, let's not over-dramatize these things. Black holes are super impressive and amazing and really cool, but we don't have to treat them like magic. All right. They are big and they are incredibly huge single objects, but that's all they are. They are single real objects with incredibly strong gravity. They are not, the be-all and end-all of the galaxy. So the first black hole we ever found, Cygnus X1, was in an X-ray binary off the Cygnus constellation, again, found using an X-ray satellite. So it's a good thing we started launching X-ray satellites, because we discovered an X-ray binary. And this is a case where we've got a massive star orbiting, it turns out, a black hole. There is mass accretion as that star overfills its Roche lobe. Mass is falling towards the black hole, towards the companion, swirling around it in an accretion disk. And that accretion disk gets hot, very hot, and so it becomes bright. And as much as we cannot see the black hole, of course, it's a black hole, you can definitely see the X-ray accretion disk around it, bright in X-rays. As for this, the first ever picture of a black hole, hopefully you remember seeing this in the news. It's made big news. This picture was taken in April 2017, and it took 2 years of work to actually publish it. This is because this picture was taken with the combined effort of 8 telescopes around the world, including one in Antarctica. All these telescopes worked together, and when you pair different telescopes working together, then what you do using a process called interferometry is you actually make a telescope the size of the distance between them. So the fact that these telescopes were spread around the world meant that we effectively made what we called the Event Horizon Telescope Project. The effective telescope was the size of our planet. And so this gave us the resolving power to read a newspaper in New York from Paris, or to take a picture of a penny sitting on the surface of the moon. This was incredible resolving power. And we used this project to take a picture of a real black hole at the heart of M87. And this is the picture. And I know what you're saying. Oh, it looks blurry. This is the best we could do? Yeah, you're damn right it's the best we could do. Do not understate this. This is incredible, this picture, okay? What this picture shows us is an empty region surrounded by a bright thing. Brighter on one side than the other for some reason. I wonder why. We're going to watch a video in a second. You might also wonder why we took a picture of the M87 black hole instead of the black hole at the heart of the Milky Way. Wouldn't that be clearer? Well, M87 is 54 million light years away, whereas the Milky Way's black hole is 50,000 light years away. So in other words, this black hole is 1,000 times farther than ours, but it's also about 1,000 times bigger, right? Because the Milky Way's black hole is 4 million solar masses. This sucker at the heart of M87 is 6.5 billion solar masses. So it's about 1,000 times farther and about 1,000 times bigger. What that means is on the sky, they would both be about the same size. The big difference then is that it's a clear view to M87, whereas the view towards the Milky Way's black hole is obscured by tons and tons and tons of interstellar gas and dust. So the Event Horizon Telescope actually did take a picture of the Milky Way's black hole. And as of this recording, they have still not revealed that picture. Okay, they managed, in 2 years, they managed to finally process the data required to reveal the picture of the M87 black hole. They still haven't finished with the Milky Ways. And one of the reasons why it took 2 years, by the way, is they had 8 different telescopes, so you have to patch together the data and make sure it's correct. Furthermore, since the telescope, one of them was in Antarctica, they took so much data, each of them took terabytes of data. It turned out that it was actually easier to load the data onto a hard drive and ship it out from Antarctica. They shipped out like pallets worth of hard drives. And they had to wait for the spring to do that from the one from Antarctica, right? So actually literally had to wait for a shipment of hard drives so they could start to do this. So anyway, it took years of work to do this, and that's the picture. So what we're going to do now is we're going to watch an explanation of what we're looking at here. A really nice video that explains in detail, and he mentions stuff like the photon sphere again, and he mentioned, so what are we looking at in the center? Is that black spot the event horizon? What is that? Why is there a hole in the center? Is that actually the black hole? Is that the center of the accretion disk? What is it? And it turns out it's none of that, actually. It's a little distorted. It's what's called the shadow of the black hole, which is slightly bigger than just the event horizon. And it's because light is so distorted as it comes around and from a black hole that you got to keep that in mind. You got to remember the distortion of light. So what we're seeing here is a representation, and it has confirmed various thoughts about what we expected to see from a black hole. In fact, as we'll watch here in this video was actually recorded right before that image was released. And he's going to show you, this is from a channel called Veritasium, which is very good. He's going to show you a picture, and he's going to say, this is what the picture should look like that will be revealed. And as you can flip back once you've watched this video, and you can see he's exactly right. That's exactly what was ended up revealing. And that doesn't mean that, oh, we went to all that hard work for nothing. What that means is we had predictions, and using our best scientific methods, we confirmed those predictions. So as well as we can prove for now we understand what a black hole should look like. And for the record, it is pretty much what you saw in the movie Interstellar. So anyway, take a look. There's the link. Take a look at this explanation of the first picture of a black hole. Okay, so pretty good. And by the way, you can watch like his follow-up videos. They're very, very interesting. So it's a fascinating thing. The shadow of a black hole ends up being slightly bigger than just a Schwarzschild radius or even just the photon sphere. And things get very, very distorted. Okay, so next class, we are going to look a little bit more at black holes, and in particular, what can happen from the material around a black hole, and the interesting things that can happen, like a gamma ray burst, when you feed a black hole, or when you form one. And then we're going to segue on into our next unit, which will be galaxies. So for example, here we see actually a picture of the central region in our galaxy. That Sagittarius A star is located roughly in the center of that. And there are jets shooting out from the central black hole. There's all sorts of interesting features. So next class, we're going to continue with a little bit more black hole related stuff, and then we're going to move on into galaxies. So you'll hear me again for that.